can get started. So thanks everyone for tuning in. I have no idea how many people are there, so it's just me speaking into a void at the moment. But thanks a lot. So basically, as Samantha just said, I've been working for ING Risk and Pricing for about just over 2 years now. Now, instead of giving a presentation where I talk about a particular project that we've recently been working on, instead, I just want to present a few cool ideas that I've seen regarding using perturbations in explainability models. So the outline of this talk is essentially, firstly, we're going to take a look at just a really simple machine learning classifier, looking at where we can and cannot trust this model. We're then going to take a brief sidestep to looking at feature importance. More specifically, we're going to take a look at the feature importance methods, or common feature importance methods that involve manipulating the data in some way. We're then going to combine these first two topics and see essentially when what happens when we start to sort of break correlations within the data, how much can we then actually trust these models that we've built. And then we're going to end the talk with looking at some fundamental LIME and SHAP packages, which are really gaining popularity right now, but how we can actually use perturbations in the data to completely fool them. So without further ado, brings me to my first main slide. So imagine a really simple machine learning classification problem. So we're trying to find, and these are the first two objects that just came to the top of my head, classifying nice little cute penguins or bassoons, right? So you've got essentially here, really simple data set. You've got mystery feature number 1, mystery feature number 2. These range from about -3 to 3 on both axes. And you can see that the gray dots are these. So these are the penguins. And the orange ones are the bassoons with some, let's say, decision boundary between these located around here. So that's all very well and good. Fit, predict the model, fine, sorted. But then imagine you come across, let's say, more test data, maybe production data, something like this, that looks like this. So what am I showing you here? So everything contained in this black box is what we've seen in this slide here. So now all we've essentially done is massively expand both of the axes for mystery feature 1 and mystery feature 2. And so a question that we really need to ask ourselves is how much can you trust what the model says? So each color here is now the model predictions. So the model says, hey, all the way down here, these are penguins, and all the way up here, these are bassoons. But can we trust anything that the model says about this? I mean, you can argue possibly that as you get closer and closer towards the black box, that the model becomes a bit more reliable. But even then, how much is it even reliable around this part? Because it has never seen this part of the data. Now, for a discussion on how to deal with models being highly certain around regions they've never seen, I really recommend checking out this video. Here, however, we're going to be focusing on what happens when you use these model extrapolations, because that's what they're doing in these regions, these extrapolations for explainability purposes. So more explicitly, looking at feature importance methods that involve interacting with the data that then leads to regions that you've never seen. So this leads me into looking at some of these feature importance methods. So we can start with permutation importance methods. So this, as far as I can tell, the first source of this is from this machine learning textbook. And this is the one that scikit-learn uses as well, the one that it implements. And the idea is pretty simple. So essentially for each feature, so you go through feature by feature of your data set D, you keep all the columns the same, except this feature, and you randomly shuffle up this feature. So as a really simple example for our mystery feature 1 and mystery feature 2, what you can do is if you permute on mystery feature number 1, this means you keep mystery feature 2 constant here, and you just shuffle this up. Now I've drawn arrows that show it going step by step, but of course it doesn't have to be like this. You can just shuffle it up like a deck of cards. And the idea is that you now take what is called your corrupted data set, you put it into your model, and you see how the model performance changes over time with this. And now the idea is that simply if the predictions of the model or the accuracy of the model now dramatically reduces, then mystery feature 1 was really important for the underlying data distribution. And similarly, if you were, for example, to shuffle mystery feature 2 and it has no effect, the idea then is that, okay, how this wasn't really that important for the underlying data distribution at all. And so you do this for all of your features, and the idea is that you see how important they are. A similar feature importance method that is used in the ELI 5, so explain like I'm 5 package, is to just instead replace this column with just random noise. Now, of course, there's different ways that you can replace data in your data set per feature. So for example, the same things that you use for, let's say, missing value imputations, you can fill with the means, fill with the medians and so on, but it's all roughly the same idea. So here you go through and again, replace feature by feature with just random noise, see how much this affects your model score as you do this. So now we're going to take a look at actually the sort of ramifications of permutations or replacing them with missing values. We're going to stick with permutations here, but also replacing with random noise or something also applies to what I'm about to say. So imagine we've got now these dots, and what we're going to do is we're going to permute this gray dot on mystery feature number 2. So this means that mystery feature number 1 is just going to stay constant. But now this point is going to essentially steal its mystery feature number 2 value from another one of these orange dots right here. So it means it will either move up or down. And in this case, you pick a random one, and in this case, it's moved down. So it was here, and now it's here. So that's all well and good. Now, a question that you have to ask yourself here is how, can this point essentially belong to the original data distribution? Now, there's all sorts of different things that you can calculate for this. You can calculate different statistical measures, so things like the Hellinger distance or Kullback-Leibler divergence, or just simple t-tests. But I think no one watching would find it overly controversial if I did something quite unscientific here, which I do not advocate doing for the validation, but just by eyeballing this point and just say, okay, it's basically with these clumps of orange dots. Fair enough, it could probably be part of the underlying data distribution. It's not overly controversial to say that. But now what happens if I have instead some correlated data? So here I forget the exact correlation parameter I used to generate this data, but obviously you can tell it's a pretty strong correlation. And so what we're going to do is again permute on this value for mystery feature number 2, meaning it will go either up or down. And let's say we permute and it moves here. And now we ask ourselves again the same question: can this point belong to the underlying data distribution? I think people would now find this much more controversial to say, if we were to just unequivocally say, yeah, sure, no problem, this is part of it, because obviously this really doesn't seem to be following the underlying trend. But this is just one point. And so what happens now if we do all of them? So we've permuted every dot here on mystery feature number 2. And you see there's some overlap for these points in the middle. So this looks okay. These could belong to the underlying distributions. But then we've got regions around here that the model has never seen, but we're asking its opinion on this. We've got regions over here that the model has never looked at. So essentially, if I just go back real quick, we are essentially in this situation here, where we're now looking at these model predictions in regions that the model has never seen. So you're essentially asking this model to really just extrapolate based on this. And so now, instead of this sort of semi-fun idea of mystery features and bassoons and penguins, let's go for a more concrete example. So let's replace mystery feature 1 with height, and then let's replace mystery feature 2 with a correlated feature. So let's say weight, right? And instead of bassoons and penguins, let's say we're trying to predict whether someone is on a professional basketball team or not. Now, if you're not careful, you can end in quite a sort of silly scenario with these permutations where, for example, the model may say, I can deal less with, let's say, 2-meter tall people who weigh 10 kilograms over here than I can, for example, with 200-kilogram babies, something like this. Now, as facetious as that sounds, if you're not careful, you can sort of end up in these scenarios. So therefore, your model says, okay, I can deal more easily with these really, really heavy babies. Therefore, weight is more important to classify whether or not someone is part of a basketball team or not, which is clearly very silly. Now, correlations are within data at the best of times a thorny issue. So you can see, for example, when you look at random forests, how they generally calculate feature importances. They have been shown to either really overweight or really underweight particular features by doing this. But I really want to show that using some of these other methods, you can really run into other risks doing this. And this actually brings me to the first paper that I want to show called, and I love the name of this, by the way, the Please Stop Permuting Features gets quite straight to the point. And I really advocate that if you have any correlations within your data, if you're using any permutation methods for generating your feature importances, I really recommend checking out this paper. Now, for a discussion, usually a presentation, I know you're not supposed to just read text off a slide to your audience. However, I think this quote here is quite important enough and sums up essentially what I've been saying for the last few minutes. So in permuting only one of the correlated features, we break its relationship with the remaining correlated features. And this results in evaluations of the function in regions which have no data nearby. Now, they actually go further in this paper. And so what they do is they generate a really simple underlying distribution, that's this y, based on 10 independent normal distribution variables, normally distributed variables. So here, we can tell just by immediately eyeballing this, right, that if we were to use some feature importance methods here, you would expect features 1 through 5 to have, they should have roughly the same importance because they've got the same coefficient. Similarly, you would expect feature number 6 to have basically no importance because it's just a 0. And then 9 and 10 should be the largest, while 7 and 8 should be close to the bottom. And that is indeed what you find when you look at cases where there's no correlations. The most important ones in this left side graph to look at are, in my opinion, the red lines and the green lines. So these are your random forests, is the green, and your neural nets that are fitted on this for the reds. However, what happens is that they then generate the same data set, but have x1 and x2 with a 90% correlation. What does this mean? Well, we then essentially end up in the same situation that we were before, where we break these the correlation patterns when using the permutation feature importance. And really crucially, what happens is that features number 1 and 2 are seen as more important than all of the other features, which should not be the case. But again, it's because you're asking your models to extrapolate into these regions that they've never seen. So what can we actually do about this? So one thing that we can do is to permute your data and then relearn the model. So in this way, what you're doing is you're not asking your model to give its opinion on a data space that it's never actually seen. Although, of course, this does involve retraining a model probably a lot of times, because you probably don't want to trust just one permutation. You probably want to do it a whole bunch of times, which means rerunning a whole bunch of models. Another example that you could use is conditioning and relearning. So here you permute your data set, but only within groups of observations. So you still try and preserve some correlation structure. And I believe this also relates to this fast leave one feature out method, which also permutes on groups of features. So if I just quickly go back, it would, for example, well, one example would be to allow permutations, for example, here, where your data points are overlapping and they could belong to the same distributions, but to then not allow this region here and not allow these regions here. I think a really important one to consider are these really simple examples, the LOCO, otherwise known as LOFO, so leave one covariate or feature out. And this is just where you discard feature by feature, rerun your model, check the new accuracy, and see how important this is. So importantly, these methods remove the overimportance of correlated features like the X1 and X2 that we saw. The only sort of downside here, which is the trade-off, is that they're computationally expensive because you're having to rebuild some more models. So now we've now basically seen how certain correlations or perturbations within the data can sort of trick us unintentionally without us realizing it. We're now going to look at how we can actually use perturbations of the data to deliberately fool other people, most notably with the SHAP and LIME packages, so how we can fool these packages. So imagine you've built a pretty complicated neural net like this one that I've just stolen from the internet. And imagine, well, here what they're doing is it seems they're predicting essentially a chemical reaction based on some image that they have. So that's fine. Imagine you've built this big neural net. It's got loads of layers. I think regardless of your neural net experience, you would have a hard time really describing exactly how your model is doing what it's doing for all of this, especially if you with each layer that you're adding, it just gets so much more complicated. So you've essentially got this black box. And of course, when you want to take your model to production and so on, you really need to describe what it is that this model is actually doing. So your goal is to describe this f of x, where x is, of course, your underlying data sets, your images in this case. And so essentially, your goal here is to explain this function. Now, recently there's become more and more popular packages such as SHAP and LIME, which are used to explain this. And what they do is that they learn an explanation model of X. Now, what you don't want is you do not want your explanation model being as complicated or as black boxy as your f of X, because in this case, all you're doing is using a black box to explain a black box. And then you essentially get this infinite regress where you never really explain the first black box that you built. So you also have this complexity parameter that you need to take into account. And so essentially what you want to do is, firstly, you want F and G as similar as possible. So G is basically doing what F is doing, but at the same time with a reduction as far as you can in this complexity parameter. So that's essentially how these packages work. But what now if we try to write a biased model? So for example, a purely sexist model or a purely racist model, and still be able to make LIME and SHAP think that it is fair. So this is a super interesting paper that I really recommend reading. Now, of course, before I go any further than this, obviously I do not advocate that you do this. I really just want to highlight the fact that LIME and Shapley are not infallible, and reading this paper and seeing how you can actually fool these techniques really helps you understand how these models can be gamed, essentially. So now assume that there is a dastardly man with a dastardly plan. That's this guy here. And his goal is to essentially deploy a model that is, let's just say, incredibly sexist. And this is going to be used for a critical decision. So I work in a bank, so let's pick a financial example. Let's say he's running a model that uses purely sex to determine whether or not someone can get a loan. So women are not allowed loans and only men are. Now, what this guy needs to do is, with your model validation, you have to provide often black box access to the customers and regulators. And they're probably going to use some of the more sophisticated packages to try and figure out how exactly this model is working, such as Shapley and LIME. And so his goal here is to fool these methods, the Shapley and LIME, to hide f of X. So even if you use Shapley and LIME, you look at it and you go, yep, seems absolutely fine to me, put this into production. How do you do that? So firstly, there are two models that you want to focus on. Firstly, we build our completely biased model that just takes, let's say, race or sex as the feature. And then we do what we're actually supposed to do, which is build the unbiased model in the first place. Now what you want to do is you actually want to take your original data set and begin perturbing it to give it a separate label. So you take your original data set, you give it a label of 0, and then you, for example, with your perturbations, you can take your original data set and permute some of the features, as we saw previously, or you can replace with random noise, or just noise some of the features and so on, as we also saw previously. And we assign these a label of 1, and you now write what's called an out of distribution classifier to try and see whether a model, a classifier, can tell whether the data belongs to the underlying distribution or not. And then you package this all up into something called an adversarial classifier. So why do you do this? So the entire point of this model is that once Shapley and LIME are used on your data set, they begin often to perturb or permute some of the data. And that's where this out of distribution classifier comes in. It will essentially realize that the data is being played with. Essentially, it thinks it's being attacked, and its sort of defense mechanism, if you want to think about it like that, is to release or deploy this unbiased model. Then once it thinks it's in production, it thinks it's seeing normal day-to-day data, it will then release the biased model. Now, just to make you aware, because of the delay, I'm going to finish in about 1 minute. So please start writing some of the questions that you have in the comments. And as far as I understand it, I will get those at the end. So basically, also in this paper, what they show is as your out of distribution classifier becomes, let's say it starts really bad. So you look at this, the race as the top feature here instead of sex. So your out of distribution classifier is really bad. This means you're always deploying your biased model because it cannot tell the difference between perturbed data and non-perturbed data. But you can see, and it's much more prominent in the LIME package here, there's a point beyond which your LIME package cannot pick up the fact that you have released a completely biased model now. And it's the same with Shapley, albeit a bit more complicated. There essentially becomes a point where you are now being able to detect differences within the data to such a strong degree that you know when LIME and SHAP are being implemented. And so you can essentially fool the people using LIME or SHAP. So just before I say thanks for listening, just to conclude, basically what we've seen is that certain correlations in the data can really cause damage if you're just blindly accepting whatever feature importance methods you're using just tell you, and not questioning exactly what it is that you're doing. And then in these cases, we've seen some methods. I really do recommend checking out the LOFO or FLOFO methods to overcome this, essentially, or to write some models to essentially use some techniques to overcome this. And so basically also be careful using any perturbation techniques when explaining your models, because even things such as LIME and Shapley, the fact that they use perturbations of the data, these can also be fooled. Now, I think these slides are going to be shared out afterwards. If not, just get in touch with me. I've put some further reading, some really interesting papers. Trying to basically papers regarding writing models in production and things like this for explainability purposes, possibly some problems within Shapley packages and things like this, which I think are pretty cool. And I've also listed all the packages mentioned in this talk if you want to check those out. But that is basically it. Please do get in touch with me if you've got any questions, anything like that. Send me some spam, and that is it. Thank you very much for listening. And now if I go back here.
So thanks a lot, Daniel.
Thank you, Daniel.
So we got actually one question in the chat, but we are not sure. I think there was one question, which hours webinar this, but I think until what time this takes. So in total, we are having talks for 1.5 hours. So for 4:30, we're done. So I have another question from Thomas. He's asking, hey, Dan, would you know of any ways to recognize when adversarial is used as a black box?
Yeah, it's really interesting. I'm not sure. I really know that I think in the future, what we're going to really see is that there probably will be need for some sort of more adversarially robust methods for this to essentially stop this. I don't know how you would write one of those off the top of my head, but I think this is going to be the sort of next level of feature explainability models. But how to actually know whether an adversarial thing is being used, I guess, I don't know, maybe eventually there's going to be sort of one person trying to use an adversarial to detect whether an adversarial is being used in a sort of battle between them, but I'm not exactly sure.
Okay, thanks. Thomas, I hope this answers your question. Another question from Yehun Kim. He says, thanks for the nice talk. Do you think it will be helpful if we rely on sophisticated permutation, depending on covariance and relying on the data generative distribution for permutation?
Yeah, I think so. I think basically if you were to use some, let's say, more sophisticated, where you really do pay attention to exactly what your perturbations or permutations are doing to the data, then it's okay. But if you're just, let's say, blindly using them just to go, yep, this is clearly the most important feature, then you can really run into issues. But like I say, with some of the other ones where you allow permutations within particular groups and things like this, then you should be fine, I believe. But it's essentially, it's more like just using it without really questioning exactly what you're asking your model, where you get the problems.
Okay.
Thank you.
Yeah, so thank you. These were all the questions. People are saying thanks a lot for your talk. Great talk. So